August 12, 1944. Rechlin Test Facility, Germany. Hauptmann Ralph Pingel climbs into the cockpit of a captured American P-51D Mustang and prepares for the flight that will shatter every assumption Luftwaffe engineers held about long-range fighter design. The aircraft, serial number 44 to 14906, captured after Captain John Winks made a forced landing near Berlin 3 weeks earlier, sits on the flight line wearing German markings. Black and white Balkenkreuz crosses cover Yusof stars. But what makes this capture invaluable isn't the Packard-built Merlin engine or the 6.50 caliber machine guns. It's the wing. German intelligence had been trying for 2 years to understand how American escort fighters were appearing over Berlin, Dresden, and Munich, cities 600 miles from Allied bases. The fuel calculations didn't work. No fighter should have that range. Bombers, yes, but single-engine fighters carrying guns, ammunition, and armor. Aerodynamically impossible. Then they tested the captured Mustang. The wing's surface was smooth as polished glass. Rivets sat perfectly flush. Panel gaps measured less than 0.5 millimeters. When Pingel flew it against a Bf-109G and Fw-190D, he discovered something terrifying. At cruising speed, the Mustang burned 30% less fuel than German fighters while flying 50 kilometers per hour faster. This is how Edgar Schmud's impossible laminar flow wing broke the laws of physics, or rather, proved German engineers didn't understand those laws as well as they thought. Before we reveal how one engineer's obsession with smooth wings changed warfare, obliterate that subscribe button. Like this video and comment which World War II aircraft amazes you most. This channel uncovers engineering secrets that won the war. Now let me show you why the Luftwaffe called this wing witchcraft in aluminum. April 1, 1899. Hildesheim, Germany. Edgar Schmud is born into a world where flight is still fantasy and heavier-than-air machines remain impossible dreams. His father runs a textile factory, expecting his son to follow into the family business. But young Edgar obsesses over something far more impractical, the mathematics of wing shapes and the physics of airflow. By age 15, Schmud has filled notebooks with wing profile sketches copied from aviation journals. He studies bird flight, measuring how different wing shapes affect gliding efficiency. The Wright brothers achieved powered flight in 1903, but aviation in 1914 remains experimental, flimsy biplanes held together by wire and faith. Schmud's family considers his aviation fixation a harmless distraction from serious education. World War I changes everything. Military demand transforms aviation from curiosity to industry overnight. Schmud watches German aircraft factories expand exponentially, hiring anyone with mechanical aptitude. At 16, too young for military service, he talks his way into a drafting job at Luftverkehrsgesellschaft, LVG, an aircraft manufacturer in Berlin. His role is menial, copying senior engineers' drawings, but it puts him inside the world he'd only read about. He learns by observing. Senior engineers design wing ribs using traditional methods. Thick leading edges, maximum camber near the front, simple curved profiles. Nobody questions why these shapes work, they're just how wings are built, based on empirical testing rather than theoretical understanding. But Schmud notices something. Aircraft with smoother surfaces and more carefully shaped profiles consistently show better performance than otherwise identical machines with rougher construction. In 1918, as Germany collapses and LVG shuts down, Schmud has acquired expertise that peacetime Germany doesn't value. The Treaty of Versailles forbids German military aviation. Aircraft factories close. Thousands of aviation workers face unemployment. Schmud makes a decision that will change his life and ultimately warfare itself. He emigrates to Brazil in 1920, seeking work in the nascent South American aviation industry. Brazil proves disappointing. The aviation work is primitive, repairing aging European aircraft, not designing new ones. After 5 frustrating years, Schmud hears about opportunities in America, where aviation is booming. In 1925, he arrives in Los Angeles with engineering knowledge, mediocre English, and determination to work in aircraft design. He finds employment at Douglas Aircraft, then at General Aviation Corporation. His English improves. His design skills sharpen. By 1930, he's working at Fokker Aircraft Corporation in New Jersey, helping Anthony Fokker, another European immigrant, build American versions of Dutch designs. The work is steady but uncreative, adapting existing designs rather than innovating. Then in 1936, North American Aviation, a small California manufacturer, offers Schmud a position as chief designer. The company has been building training aircraft and light bombers but wants to break into the fighter market. They need someone willing to try unconventional approaches. Someone not bound by the way things have always been done. Schmud accepts immediately. In 1938, Schmud attends a lecture at the California Institute of Technology by Theodor von Karman, the Hungarian aerodynamicist who would become America's leading theorist on fluid dynamics. Von Karman presents research conducted by the National Advisory Committee for Aeronautics (NACA) on something called laminar flow, a phenomenon where air flows smoothly over a surface in organized layers rather than turbulent chaos. Most wings in 1938 experience turbulent airflow almost immediately after air contacts the leading edge. This turbulence creates drag, the resistance that requires engines to work harder to maintain speed. But NACA researcher Eastman Jacobs has discovered that precisely shaped airfoils can maintain laminar flow much farther along the wing surface, dramatically reducing drag. The catch: the wing profile must be radically different from conventional designs. Traditional wings reach maximum thickness at roughly 30% of the chord, the distance from leading edge to trailing edge. Jacobs's laminar flow airfoils place maximum thickness at 45 to 50% of the chord, far back from the leading edge. To conventional engineers, this looks wrong. Wings should be thick in front for strength and thin toward the back for clean airflow separation. Jacobs is proposing essentially the opposite. More problematically, laminar flow requires surface smoothness measured in microns. Any rivet heads protruding into the airflow, any panel gaps, any paint imperfections, all would trip the boundary layer from laminar to turbulent flow, negating the entire advantage. The manufacturing precision required seemed impossible for mass production. NACA's experimental laminar flow wings worked in wind tunnels on carefully polished models. But translating that to production aircraft was another matter entirely. Schmud sits in von Karman's lecture taking notes furiously. Other engineers dismiss laminar flow as impractical theory, interesting science that won't survive contact with production reality. Schmud sees something different. He sees the solution to the fundamental problem plaguing fighter design. Range. Fighters in 1938 are fast and maneuverable but have pathetic range. The best German fighters, the Bf-109E just entering service, can fly perhaps 400 miles on internal fuel. British Spitfires achieve similar numbers. American designs are no better. Fighters escort bombers for maybe 200 miles, then must turn back, leaving the bombers vulnerable. Strategic bombing doctrine assumes this limitation is permanent because physics demands it. But what if you could reduce a fighter's drag by 30 to 40% through laminar flow? Suddenly the same fuel load carries the aircraft twice as far. Or the same range requires half the fuel, allowing more ammunition and armor. This isn't an incremental improvement, it's a revolutionary advantage. May 1940. The British Purchasing Commission approaches North American Aviation with an unusual request. Britain is at war. Their aircraft factories are operating at maximum capacity but cannot meet demand. The Commission wants to license-build Curtiss P-40 Warhawks at North American's facilities. The proposal makes financial sense: guaranteed contracts, proven design, minimal risk. Schmud's boss, company president James Dutch Kindleberger, considers the offer, then makes a counterproposal that borders on insane. Instead of building someone else's fighter, let North American design and build a completely new fighter from scratch. Better than the P-40. Better than anything currently flying. And they'll deliver the first prototype in 120 days. The British representatives think this is either arrogance or delusion. 120 days from start to first flight. Established manufacturers take years to develop new fighters. Kindleberger turns to Schmud. Can you do it? Schmud has been waiting years for this question. Yes, but not with a conventional design. He explains laminar flow airfoils, the NACA research, the potential for revolutionary range. Most engineers in the room look skeptical. Laminar flow is theory, and proven in combat aircraft. Hideously difficult to manufacture. Why risk everything on untested concepts when conventional designs work adequately? Because adequate isn't good enough, Schmud argues. The British need fighters that can escort bombers deep into Germany. Current fighters can't do that. Build them a conventional design and they'll have another short-range fighter that doesn't solve their problem. Build them something revolutionary and North American establishes itself as a premier fighter manufacturer. Kindleberger makes the decision that will create aviation legend. Do it. You have 120 days. Schmud assembles a design team and begins work immediately. They call the project NA-73, North American's internal designation. The British will call it Mustang, though that name won't be chosen for months. Every decision Schmud makes prioritizes the laminar flow wing. He chooses the NACA 45-100 series airfoil, a radical profile with maximum thickness at 45% chord. The wing will be thin, smooth, and precisely manufactured. No protruding rivet heads. No rough panel joints. Every surface flush riveted and polished. The production engineers warn this will be expensive and time-consuming. Schmud doesn't care. The aerodynamics demand perfection. The wing's internal structure presents enormous challenges. Traditional wings use ribs and spars with metal skin riveted over the framework. The rivet heads protrude slightly, creating exactly the surface roughness that kills laminar flow. Schmud designs a completely different approach. The skin itself becomes structure through careful metal forming and strategic reinforcement. External rivets are either eliminated or countersunk so deeply that the wing surface remains smooth within 0.13 mm tolerance. The fuselage gets equal attention. Schmud designs it around the British Allison V1710 engine the contract specifies, creating a streamlined shape with minimal frontal area. The radiator, typically a major source of drag, is placed underneath the fuselage with ducting designed to create thrust rather than just drag. The concept, called the Meredith effect, uses the radiator's waste heat to slightly accelerate air through the duct, recovering some of the cooling drag as forward thrust. 102 days after starting, North American rolls out the NA-73X prototype. Schmud has delivered 18 days early. The aircraft is beautiful in a way fighters rarely achieve. No bulges, no protuberances, every curve flowing smoothly into the next. Test pilot Vance Breeze flies it on October 26, 1940. The aircraft performs exactly as Schmud calculated. At 370 miles per hour, it's faster than the P-40 Kindleberger almost licensed. The climb rate exceeds expectations. The handling is described as viceless. No bad habits, no unexpected behaviors. But there's a problem. The Allison engine the British specified lacks a supercharger optimized for high altitude. Above 15,000 feet, performance drops dramatically. The RAF accepts delivery of the first Mustangs in October 1941 and assigns them to low-altitude tactical reconnaissance and ground attack. Schmud's laminar flow wing is working perfectly at low altitude. RAF pilots report the Mustang is fast, stable, and has phenomenal range for a fighter. Some pilots fly 500-mile missions and return with fuel remaining. But strategic bombing happens at 20,000 to 30,000 feet, where the Allison engine gasps for air and the Mustang becomes mediocre. The breakthrough comes from an unexpected source. In April 1942, Ronald Harker, a Rolls-Royce test pilot, flies a Mustang at the RAF's Duxford airfield. He immediately recognizes that the airframe is extraordinary but limited by its engine. Harker writes a report to Rolls-Royce management. Pair this American airframe with our Merlin 61 engine, the supercharged power plant developed for high-altitude Spitfires, and you'll create the best fighter in the world. Rolls-Royce engineers are skeptical. The Merlin is heavier than the Allison, physically larger, and produces different vibration characteristics. Mating it to an airframe designed for a different engine risks destroying the Mustang's careful aerodynamic balance. But Harker's enthusiasm convinces them to try. They obtain 5 Mustang airframes and install Merlin 61 engines. The first Merlin-powered Mustang flies on October 13, 1942. Test pilot Jeffrey Quill, Supermarine's chief test pilot who has flown every Spitfire variant, takes it up for initial evaluation. When he lands 90 minutes later, his report is emphatic. This aircraft is faster than the Spitfire 9 at all altitudes, has better range than any fighter he's flown, and handles beautifully. The combination of Schmud's laminar flow wing and Rolls-Royce's supercharged engine has created something unprecedented. The numbers are staggering. Maximum speed, 440 miles per hour at 28,000 feet, 50 miles per hour faster than contemporary German fighters. Combat radius on internal fuel, 400 miles, twice what German or British fighters achieve. With external drop tanks, 850 miles. This means a Mustang can escort bombers from England to Berlin and back, a mission profile previously considered impossible for single-engine fighters. The U.S. Army Air Force, which has been skeptical about the British-designed Mustang, suddenly takes intense interest. They order the P-51B variant with the American-built Packard Merlin V1650 engine, essentially a license-built Rolls-Royce Merlin. Production begins in mid-1943. By December 1943, P-51Bs are escorting B-17 and B-24 bombers over Germany. The impact is immediate and catastrophic for the Luftwaffe. For 2 years, German fighters have attacked American bomber formations with relative impunity once the short-range P-47 Thunderbolts turn back. Now Mustangs appear over targets 600 miles from Allied bases, staying with the bombers throughout the mission. Luftwaffe pilots expecting easy kills find themselves fighting long-range escorts with better performance than their own fighters. August 12, 1944. Captain John Winks of the 361st Fighter Group engages Bf-109s near Berlin. His Mustang takes cannon hits that damage the engine cooling system. Coolant temperature rises dangerously. Winks realizes he can't make it back to England and decides to force land rather than bail out over Germany. He brings the Mustang down in a field near Oranienburg, 20 miles north of Berlin. The landing gear collapses, but the aircraft remains largely intact. Wehrmacht soldiers arrive within minutes. Winks becomes a POW. His Mustang becomes the most valuable intelligence prize the Luftwaffe has captured in months. German recovery teams transport the captured Mustang to Rechlin immediately. Luftwaffe High Command issues orders identical to those for the captured Spitfire 2 years earlier. Highest priority evaluation, maximum security, complete analysis of all systems. But this time, the focus is different. They understand American armament and engines reasonably well. What baffles them is the range. Oberst Edgar Peterson, Rechlin's technical director, briefs his analysis team on August 15. Gentlemen, the Americans are escorting heavy bombers to Berlin and beyond. Our calculations show this should be impossible. A single-engine fighter cannot carry sufficient fuel for 1,600-kilometer missions while also carrying weapons, ammunition, and armor. Yet they are doing it. This aircraft will tell us how. The Mustang arrives at Rechlin on August 17. Technicians begin methodical inspection, measuring and photographing every component. The first shock comes when they weigh the aircraft. Empty weight, 3,465 kilograms. A Bf-109 G6 weighs 2,700 kilograms empty. But the 109 carries only 400 liters of internal fuel. The Mustang carries 732 liters internally, plus provisions for 568 liters in external drop tanks. Yet somehow, despite carrying nearly twice the fuel capacity, the Mustang weighs only 28% more. The wing holds the answer and the mystery. Luftwaffe engineers examine the profile carefully. Maximum thickness at 45% chord, far behind conventional placement. The entire surface is smooth as polished metal. They use precision gauges to measure surface irregularities. Less than 0.10 millimeters across the entire wing. German production standards consider 0.50 millimeters acceptable. The Americans are manufacturing to tolerances 5 times tighter. Oberingenieur Hans Multhaupt, Focke-Wulf's chief aerodynamicist temporarily assigned to the evaluation, runs his hand along the wing's lower surface. "This is theoretically impossible to produce in quantity," he mutters. "Each wing must take hundreds of man-hours to achieve this smoothness." Production engineers check. American factory specifications call for flush riveting, reamed holes, and surface finishing on every Mustang wing. North American is building thousands of these aircraft monthly. Somehow, impossibly, the Americans have industrialized precision that German manufacturers reserve for experimental aircraft. The laminar flow principle becomes clear when engineers study NACA research papers captured from a downed B-17. The papers describe extensive wind tunnel testing of various airfoil shapes, measuring exactly how airflow behaves over different profiles. The Germans have the theoretical knowledge. Boundary layer theory has been understood since the 1920s, but they never attempted to exploit it in production aircraft because the manufacturing precision seemed unattainable. Fuel consumption testing begins on August 24th. Mechanics install calibrated fuel flow meters and run the Packard Merlin at various power settings. The data is stunning and depressing simultaneously. At 25,000 feet, cruising at 350 kilometers per hour, the Mustang consumes 242 liters per hour. A Bf-109 G6 at the same altitude and speed consumes 340 liters per hour. The Mustang is 30% more fuel efficient despite being heavier and faster. The difference is drag. The Germans calculate the Mustang's total drag coefficient at approximately 0.0163 to 40% lower than the Bf-109's 0.0270. This single number explains everything. Lower drag means less power required to maintain speed. Less power means less fuel consumption. Less fuel consumption means vastly extended range. The laminar flow wing, combined with the Mustang's streamlined fuselage and careful detail design, has created a fighter that simply slips through air with minimal resistance. Flight testing begins on August 28th. Hauptmann Ralph Pingel, who tested the captured Spitfire 2 years earlier, climbs into the Mustang's cockpit. The aircraft has been repainted with Luftwaffe markings. Black crosses on fuselage and wings, yellow identification bands, white number 24 on the tail. The captured Packard Merlin has been thoroughly inspected and cleared for flight. Security around the test remains extreme. Luftwaffe fighters patrol overhead to prevent Allied reconnaissance from spotting the prize. Pingel's first flight lasts 85 minutes and covers basic handling characteristics, takeoff and landing performance, control harmony, and initial impressions. His written report, filed that evening, opens with an extraordinary statement. This aircraft represents the most significant advance in fighter design I have evaluated. It combines performance, range, and handling qualities that redefine what is operationally possible. The comparative trials against German fighters begin September 1st. First matchup: the captured Mustang versus a Bf-109 G6, the Luftwaffe's primary frontline fighter in late 1944. Both aircraft take off simultaneously and climb to 7,000 meters. In mock combat, the Mustang demonstrates clear superiority in every parameter except initial climb rate below 4,000 meters. It's faster at all altitudes, turns tighter, rolls faster, and accelerates better in level flight. The 109 can only compete by using vertical tactics, climbing steeply to gain energy advantage, but this burns fuel the German fighter cannot spare. Against the FW-190D9, the newest Luftwaffe fighter entering service, the results are similarly discouraging. The Focke-Wulf matches the Mustang's speed at most altitudes and possesses superior roll rate, but the American fighter still turns more tightly and has vastly better range. More critically, the FW-190D's BMW 801 radial engine consumes fuel voraciously. In a sustained engagement, the German fighter will run dry first, forcing disengagement regardless of tactical situation. But it's the cruise efficiency testing that truly shocks Rechlin's engineers. They fly the Mustang on a simulated escort mission profile, climb to 7,500 meters, cruise at 480 kilometers per hour for 2 hours, conduct 15 minutes of combat maneuvering at full power, then cruise home for 2 hours. Total time: 4 hours 15 minutes. Total distance covered: approximately 1,800 kilometers. Roughly the distance from England to Berlin and back. The Mustang lands with 120 liters remaining, enough for 30 minutes of additional flight. A Bf-109 G6 attempting the same profile runs dry after 650 kilometers. An FW-190D9 makes it 720 kilometers. The Mustang's range advantage isn't marginal. It's transformational. This explains why American fighters are appearing over targets German intelligence calculated were safe from single-engine escort. Oberst Peterson's summary report to Luftwaffe High Command, dated September 8, 1944, is brutally honest. The enemy possesses a fighter that can escort heavy bombers to any target in Germany while maintaining combat capability throughout the mission. Our fighters cannot prevent this. We can inflict losses, but we cannot force the escorts to withdraw due to fuel limitations. The Americans have solved the strategic escort problem through superior aerodynamic engineering. The report specifically highlights the laminar flow wing as the critical technological advantage. German engineers understand the principle but lack the manufacturing capability to replicate it. Implementing the precision tooling, quality control, and production techniques required would take years and resources Germany no longer possesses in late 1944. The Rechlin evaluation triggers immediate tactical responses across the Luftwaffe. Jägerschwader commanders receive updated directives emphasizing that engaging P-51 escorts should be avoided whenever possible. Instead, German fighters should attempt to bypass escorts and attack the bombers directly, accepting casualties from escort fighters as preferable to prolonged dogfights that favor the Mustang's superior endurance. But this defensive posture acknowledges a fundamental shift in the air war. For 3 years, the Luftwaffe held range advantage over RAF and early Uzov fighters. German pilots could choose when to engage, breaking contact when fuel ran low, knowing British and American escorts would turn back first. The Mustang reversed this calculus completely. Now German fighters must disengage while American escorts still have hours of fuel remaining. The psychological impact cannot be overstated. Luftwaffe pilots who had grown accustomed to Allied escorts withdrawing halfway through missions suddenly face opponents who stick with bomber formations all the way to target and back. This persistent presence forces German fighters to operate at maximum intensity throughout bomber streams, burning fuel at combat power settings while Mustang pilots can cruise efficiently between engagements. Aircraft development priorities shift in response. Tanks Ta-152, designed for extreme high-altitude interception, receives accelerated development funding. Messerschmitt's Me-262 jet fighter program, previously controversial due to Hitler's bomber conversion demands, gains renewed support as the only aircraft with sufficient speed advantage to potentially offset the Mustang's range superiority. But these programs cannot produce combat-ready aircraft in time to affect the war's outcome. Meanwhile, P-51 production in America reaches industrial scale. By the end of 1944, North American aviation is producing over 500 Mustangs monthly. Every fighter group in the 8th and 9th Air Forces transitions to P-51s. In the Pacific, despite the longer overwater distances, P-51s begin escorting B-29 missions against Japan from Iwo Jima, another operational capability previously considered impossible. The kill ratios tell the story. P-51 pilots in Europe achieve approximately 11-to-1 kill-to-loss ratios against Luftwaffe fighters, among the highest of any Allied fighter type. This isn't solely due to pilot skill or aircraft performance. It's the operational freedom that strategic range provides. Mustang pilots can choose when to engage, when to disengage, and when to aggressively pursue damaged enemy fighters, knowing they have fuel reserves German pilots lack. Edgar Schmud never learns about the Rechlin tests during the war. Security classifications keep German technical intelligence reports secret until the 1970s. But Allied technical intelligence officers examine captured Luftwaffe documents after Germany's surrender and discover detailed analysis of Mustang construction, particularly the laminar flow wing. One German report concludes, "This wing represents manufacturing precision we cannot replicate with current production methods. The Americans have solved problems we considered unsolvable." Schmud's design proves remarkably adaptable. The P-51H variant, developed late in the war, incorporates an even more refined laminar flow airfoil and lighter construction, achieving 487 miles per hour maximum speed, faster than many early jets. The civilian racing variants that dominate post-war air races consistently break speed records. Even in the 1970s, highly modified Mustangs remain competitive in unlimited air racing, 6 decades after Schmud's initial design. The captured Mustang at Rechlin survives until April 1945, when advancing Soviet forces forced German personnel to evacuate the facility. Rather than let the aircraft fall into Soviet hands, Luftwaffe technicians destroy it with explosive charges. The Americans whose fighter it once was would never know that German engineers considered it the most revolutionary aircraft they'd examined during the entire war. Edgar Schmud remains with North American aviation through the 1950s, designing the F-86 Sabre, the jet fighter that dominates Korean war skies. The Sabre incorporates lessons learned from the Mustang, particularly regarding clean aerodynamics and careful detail design. Schmud retires in 1960, having shaped 2 generations of American fighter development. He dies in 1985 at age 86, his contributions finally receiving recognition in aviation history books. The laminar flow wing concept he championed remains controversial among engineers even decades later. Post-war wind tunnel testing reveals that perfect laminar flow rarely occurs on operational P-51 wings. Combat damage, wear, environmental contamination, all disrupt the carefully maintained smooth surfaces. Some engineers argue the Mustang's exceptional performance came primarily from its overall clean design rather than laminar flow specifically. But this misses the larger point. Whether or not perfect laminar flow occurred in combat, the pursuit of that goal forced unprecedented manufacturing precision. North Americans' quality control standards, developed to achieve laminar flow tolerances, produced aircraft with dramatically lower drag than competitors, regardless of whether the boundary layer remained perfectly laminar. The theory may have been partially incorrect, but the results were undeniably revolutionary. Modern computational fluid dynamics, unavailable to Schmud in 1940, confirms that P-51 wings did maintain some laminar flow, particularly over the first 30 to 40% of chord under cruise conditions. Not the 60 to 70% NACA predicted, but still substantially more than conventional wings of that era. Combined with flush riveting, careful panel fitting, and refined contours, this produced the drag coefficient that shocked Rechlin engineers. The strategic impact is beyond dispute. Bomber losses over Germany dropped dramatically once P-51 escorts reached operational status. In February 1944, before P-51s achieved numerical superiority, 8th Air Force lost 6.2% of dispatched bombers per mission. By June 1944, with P-51s dominating escort duties, losses fell to 2.4%. The Luftwaffe lost air superiority over Germany not solely because American pilots were better, though many were excellent, but because they flew fighters that could stay with bombers throughout missions that German fighters couldn't sustain. General Hap Arnold, commanding general of U.S. Army Air Forces, later wrote, "The P-51 Mustang was decisive in winning the air war over Europe. It gave us the range to escort bombers anywhere in Germany and the performance to defeat any opposition. The Mustang made strategic bombing feasible. Today, over 150 P-51 Mustangs remain airworthy, more than any other World War II fighter type. They dominate warbird shows and air races, celebrated for their elegant lines and thunderous Merlin roar. Each one testifies to Edgar Schmud's belief that unconventional thinking could produce revolutionary results. That German engineer who once sketched wing shapes in Hildesheim became the American designer who created the aircraft that helped defeat Germany. The laminar flow wing he championed, dismissed as impractical theory by many engineers, became the foundation of the most effective escort fighter in history. The manufacturing precision considered impossible in 1940 became standard practice by 1944. The P-51 Mustang. Designed in 120 days. Powered by a British engine. Built with a wing that shouldn't have worked but did. The fighter that taught German engineers at Rechlin that sometimes theory works better than they calculated, when someone has the courage to try it.